Hello everyone, my name is Hania Zarafshani. I'm a researcher at imec, and today we will discuss about the introduction of the life cycle assessment. First, we will discuss about what is the problem that brings us here in this webinar. Then we will discuss about what is sustainability as a potential solution to this problem, and LCA as the main standard method for fulfilling the sustainability, which is the main body of today's presentation. Then we will finalize the presentation from my side with some practical challenge that we have in this regard. Let's start with the fact that what is the problem? Well, the problem is not new to you all. We all know that the climate change is today's problem. The reality is that the amount of the CO2 that we produce now is more than the amount that that the earth can absorb it. Just today, the amount of CO2 that we produce is about 430 ppm. And if you're wondering what does it mean? It means about 1.5 degree centigrade above pre-industrial time. And I have a good news here. The good news is that although that we are all aware of this problem, there is some solution for this problem. There are different mitigation to answer to this problem. And but as you can see in this figure from IPCC, the cost and feasibility of different mitigation to answer to this climate change problem is different. And you should see this different mitigation in a way that they are not possible to adding to each other, and we should see it as a portfolio of the solutions. And here where LCA comes to the story to enables us to assess different mitigation to see that which option is much more better with the less with the less cost and higher feasibility. But let's look more in details of this graph. One part is specifically interesting for us that we are in industry, that we can see that industry is a part of this mitigation approach. So in just industry itself, not the energy or transport. And in this aspect, we as we are in semiconductor industry, we can have two roles. In one aspect, we can work on enabling the decarbonization of the other sectors, for example, by electrification, sensing, computing to help other sectors to reduce their impacts. In another hand, we ourselves are responsible to decrease our environmental footprint. So now that we realize that we are worried, but we want to take actions. And in this aspect, Genesis is a European collaboration project that's its aim is to put effort to answer some of these problems. And this project tries to answer from data to insightful actions. And specifically in the work package 1, we will try to help the partners, and we will try to enable us to measure our impacts by the help of LCA model, enabling the importing the environmental aspect in the power, performance, area, cost analysis in order to distinguish where is the hotspot of our analysis, where we can improve, and have a trade-off of the analysis and prioritize our efforts in a construction way, and finally act in this way, in the correct way. And specifically today, we will focus on the LCA model as a measuring tool. So let's start with asking this question that what is sustainability, and why we think that sustainability can be a very good answers to the climate change problem. Well, as is defined in 1987, sustainability is the trade-off across 3 different dimensions: environmental, economic, and social. And its aim is that we want to answer our today's need, but without compromising future generations. So the aim is that we want to fulfill our aims in the environmental, economic, and social aspects, but it is important that our children needs to be able to answer their needs too. And what does it mean for us as engineer? For us, in practice, it means that we need to deliver the required function while minimizing the life cycle impacts. And it is important to mention that sustainability is not a label, it's a measurable performance under clearly stated assumptions, which means that we cannot say that this product is sustainable. Sustainable is not a label. And here today we are here to realize that how we can have the measurements on sustainability. We were on this slide to discuss that we talked about what is sustainability. Another things that we want to introduce is sustainability materials management. And here our focus is that when it comes to the sustainability, we look at the combination of the environmental, technology, and economic aspects at the same time. And what does it mean? It means that in general, how we look at this picture, we see it as the fact that the resources, fuels, and land comes from the sources from what we call as biosphere. Let me be sure that I have my laser. Yeah. The resources, fuels, and land enters to the technosphere and circulate in the economy to enable to produce a valuable materials. And after that, the waste emissions again go to the biosphere. So in sustainability materials management, the aim is to reduce the imported input from the biosphere as possible, reduce the waste emission as possible, and tries to enable the technosphere to capture the valuable materials inside the economy as possible without reducing the quality of the materials. To help me understand that how much familiar you are with the sustainability, I would like to ask you to have a quiz with each other, if you do not mind, to scan this QR code, if you do not mind, and answer to this question that which option do you think has the lower environmental impacts? If you do not mind. So I would like to ask you to scan this QR code and answer to this question. Great. So I will go to the second question, which is somehow similar, which is something that now in the source we are trying to think what is the best option. So my main message here, as you can see, even in these two very simple, sensible questions, the range of the answers that we could receive, how variant it is. And to just give you the correct answer for both of them, the answer is, as most of you think, is it depends. Why? Because it depends that which environmental aspects we are looking for. For example, in the case of the car, electrical cars, it is true that they are much greener in the CO2 emissions, but they require some raw materials that they are not green in some other environmental impacts. So by having these two questions, that they are even from the materials, from the process, from the technology that we have sense about it, we realize that it is necessary to have a standardized approach to assess the sustainability. Otherwise, we need to come to these questions and talk about it for several hours to see that how did each of group think and assess and think that that option is more greener. So this is why we need a standardized approach to assess the sustainability. But how do we want to have that? How do we want to measure the sustainability now that we know that it is important to assess it? LCA is an ISO framework that answers to this need. It is a standardized framework to quantify life cycle input-output and translate them in potential environmental impacts for a defined product system. Why it is important? As I mentioned, the first importance is that it helps us to have a like-for-like comparison. When I ask what is the better option, environmental perspective, electrical car or gasoline car, we need to have a framework to assess both option and answer to this question. So it helps us to have a like-for-like comparison. Another importance is that it helps us to avoid burden shifting. What does it mean? It means that we do not want to just improve the scope, the parts that we want, but just transfer the impact to another process. We want to have a holistic overview and decrease the environmental impact totally. Another importance is that it helps us to reveal the hotspots. We as engineer want to know that which part of our process is more important and is more environmental impacts more that we want to focus on that and improve on that. We want to prioritize our efforts. And where does the LCA helps us in designing of the material, architectures, process, improving, as I mentioned, defining where is the hotspots and where is the optimization points, and talking about the end of life, that which recycling and disposal approach is better. And LCA also helps us to track the product and site company trends. LCA has four stages: goal and scope, inventory, impact, and interpretation. But it is important that from the beginning, we know that it is not a one-time step. It is very iterative. During the analysis of the LCA, we may do these steps several times from goal and scope to interpretation. We will move from the first step to the end and again start over. But now let's start with the first stage of the LCA, which is goal and scope. As it is obvious from the name of the goal and scope, it means that in goal and scope, we assess our goal and scope. In goal, we want to see that what is the purpose of doing this LCA? What is the question that you want to answer? The question should be shaped really sharp, that what is the aim of this LCA? What is the audience of this question? Why it is important for us? Because lately, when we have the answers of the questions, we need to be sure that it is the answer that the audience at the beginning of the LCA can appropriately will receive it and apply it. And what is the use of this LCA? What is why we are doing again this LCA? In the scope, we will define our functional unit, system boundary, modeling choice, impacts, and data. What does each of these terminology means? We will discuss. The main outputs of the goal and scope stage is a transparent, reproducible study plan. What does it mean? When you are doing the LCA, it is important that document all of our assumptions and all of this information, because anyone after us that wants to check our LCA or wants to benefit from our LCA needs to know that what was in our mind. And by just reading our document, he or she should be able to redo all of the stages again. As an example of the scope, when I say the system boundary, for example, our system boundary can be the process that starts from upstream and the fab tool and abatement part. We capture this system boundary, and after that, we calculate the impact per wafer. And the key set of choices that we select in the scope is our study object, our functional unit and reference flow, that what is this study? For example, it is per wafer, it is per step. What is our boundary? What is the data that we use? What is our final impacts that it is interesting for us to assess? And what is the quality of our data that we are using then? An example of the goal can be that we want to compare two exhaust greenhouse gas abatement options and quantify per wafer impacts. So it can be a kind of research question that LCA can be made on top of that. Another thing that we need to discuss about here is that we have different system boundary, different life cycle variants. We know that our value chain starts from raw materials and end with end of life. If our LCA focus on all of the stages from raw materials to the end of life as a linear that we say that we start from these materials and end with end of life, what we call it is that we are doing a cradle to grave analysis. If we just focus on the from the raw materials and until the gate of our manufacturing, we call it a cradle to gate, which what we are doing is that we are excluding use phase and end of life. And if our focus is just optimizing a process or a part in our manufacturing, we call it gate to gate, which in this stage we need to link the information with upstream and downstream data. The last one is cradle to cradle, which what is the difference between the first one and the fourth one? Which basically in the first one we look at the information or the boundaries as a linear. We start from the raw materials and end with the materials with end of life, that we say that here it is the end of the process. But in the fourth one, we look at as a circularity of that. After that, we even care that when even it is the end of the process, what is happening to that? For example, can we recover some of our materials to return and use it as a raw materials or not? And it is very important that when we are comparing two process or two technology, we need to have the same system boundaries. As an example, for example, in this example of the cars that we mentioned, gasoline car and electrical car, the question that we need to answer and we need to specify is that are we just focusing on the manufacturing cars? Or no, we are also considering the use phase of this car, that mainly for example, electrical car is greener. Or we also considering the end of life, that for that we need to we think that how we want to take care of the batteries in the electrical car. So the next thing that we want to talk is that we need to define in the goal and scope is functional unit and reference flow. We need to say that what is this LCA, what is the quantified amount of this LCA? What is the LCA for? Now that we define that what is the scope of this LCA, we need to define what is the quantified performance of a product system used as a reference unit. And after that, define what is the input and output to deliver this performance. Basically, the reference flow is the scaling factor that links the functional unit to the lifecycle inventory. To give you an example and give you the sense that what does the functional unit means, for example, the functional unit can be etching of one 300 millimeter wafer layer to a specific specification. Why we need to report all of these quality performance of the etching when we are talking about the functional unit? Because all of them later on illustrate that what is our input and what is our output. So we need to have the transparency in the fact that what is our functional unit and what is the different quality of our functional unit. And the key idea is here is that we need to express every inventory flow and every impact results per functional unit. Let's go to the more interesting part, I would say, for us as engineer, which is the inventory part. The first thing in the inventory is talking about what is the unit process. Well, first, before starting anything in the inventory, in the providing the data for LCA, it is important to mention that what is this information for. So we do not just put all of the information in a black box. Rather than that, we just define a small building block. We call it unit process, and we say that what is all of the inputs that comes to this unit process and what is the product of it. So it is important to have a clear boundary of all of the information about the unit process. As an example, in this value chain, the manufacturing step can be a unit process. And our role here as engineer is that we clearly process map and equipment list for this unit process. Capture and measure all of the energy and utilities for this unit process, and record all of the operating mode and data quality for the specific unit process. Now that we define what is our unit process, we need to have the bill of the materials and energy and say that what is all of the inputs and what is all of the outputs for this unit process. As an examples for the input, we can discuss all of the energy, material, chemicals, and the waters that comes to this unit process. And as an example of the outputs, we need to capture all of the air emissions, wastewater, and solid waste that comes out of this unit process. And what each of them mean. For example, as an example of the energy, in energy, the key data that we need in LCA is the measured energy use of the tool and powers. And we as engineer, what is our role? As our role is to separate processing, waiting, and standby states to be able to later on have a good impact assessment and have a good calculation. And I will not go to details of each of them because later on you will have this slide. But in each of the inputs and outputs, we need to have a specific data in order to have all of the information for this unit process that later on will be used for calculations. In life cycle inventory, we mainly use two different data sources. First, what we call foreground data sources, which is the information for assessing the product, process, or site-specific, which mainly I talked about it in the previous slide. So this data is all of the data that we capture, we measure. It is on our hand. It is based on measurement logs or engineering models. And it is best for key contributors and variable steps. But another source of data is generic data from literature and database, which we usually use for upstreams and downstream process. So it is somehow collecting the data that we cannot measure. And if you are just wondering that how they are connecting with each other, well, first we measure and collect all of the information for our process, which we call it foreground. And then we build a life cycle inventory, which I talked about it in the previous slide, which means that we have the bill of materials and energy. Then we link it to the database, background database, to have the whole picture, and then we calculate our assessments. The key idea here is that foreground data define your system, background data fill the rest of your life cycle. To go more in detail that what is foreground data, that because it is important to understand it because we measure it, all of the information that is related to the direct metering, factory likes, equipment supplier, engineering models. So our contribution as engineer in providing this foreground data is that provide preliminary foreground process data. But just the data is not enough. We need to provide this information that what is the allocation of the shared flows across tools, because we know that the process and the manufacturing is too complicated. It is not just one input, one output. Usually, the output goes to different process, and we as engineer, because we are building this process, we need to document what is the allocation of each input and output. And we need to validate all of the range and system boundaries that is happening in this unit process and in this story. The common constraints that we have in this regards is, first of all, confidentiality, because all of this data and this information is basically the recipe of the process, that some of them are confidential. And the second one is the temporal variability. So the values may change over time. And it is important to keep in mind that when we are reporting the information of the foreground, use a range for that. Avoid using single values, because for the measuring and for everything, whenever that we calculate, the value may range. So it is important to keep to report the values as a range. It is important to run conservation checks at each model and record the metadata, record what is the geographical information related to this data, year, technology, and why it is important, this information. Later, in this slide, when we now want to connect this inventory to the background, we need to connect the points correctly. We need to connect the foreground that we collect with the background database, with considering that we are connecting to the correct geography, time, technology, and system model. So in the previous slide, we correct everything. We build the lifecycle inventory. Now our role is to link this to the correct background databases. Some famous background databases that usually we use is EcoInvent, the United States Lifecycle Inventory, which is mainly for United States, the Gabi databases, and Exobase. So the third steps in the life cycle impact assessment is to calculate this information, the impact of this flow and impacts of this information that we already gathered in the previous step. So just to give you again a summary in the goal and scope, we say that what do we want to assess in the inventory? We gather all of the information that we want to calculate the impact, and now it is the calculations parts. So the aim of the lifecycle impact assessment is translating the inventory that we built in the previous sections into impact indicators. And how do we do that? We bring the information from the inventory and classify the flows. We apply the characterization factors to the different flows, and then we simply report the indicators. The core logic behind the lifecycle impact assessment is to map flows to different categories, apply characterization factors, and optionally do the normalization and weighting. And the typical output, for example, to give you some idea that what is the output of the lifecycle impact assessment is, for example, kilogram CO2 equivalent, which is the final indicator for climate change, and information related to the hotspot, that where is the parts that we can improve. Basically, life cycle impact assessment turns inventory into indicators, but results still depend on the method choice and data quality, because it is important that what is the method that we select in life cycle impact assessment. As I mentioned, we have 4 steps in life cycle impact assessment: classification, characterization, normalization, and weighting. We will start with the classification, which basically we map each flow to the impact categories. Then in the characterization, we use multiple characterization factors to calculate the indicators. Then in the optional steps of the normalization and weighting, we compare to a reference in the normalization, and we value to our indicators in the weighting. In the classification, what we do is that we start with the elementary flow that we have as the output of the inventory, and we need to group them to the different impact categories. For example, climate change, acidification, eutrophication, resource and land use. And here, the practical tips here is that we need to be careful about the correct components, that it is emitted to air, so it goes to the climate change, but what is the source of different elementary flow, to do not mix them, do not mix the source. We need to avoid double counting here. and be sure that the method is consistent for all of the impact categories. Then we need to characterize, we need to calculate, convert inventory flows in the previous and apply them some characterization factors to calculate the impact categories. Basically, for having a simple indicators, what we need is we need to sum the flow amount to the characterization factor. Here, this characterization factor, you may wonder that how we will find it. This characterization factor, it is important that it depends on the mechanism that we are discussing, about the location, about the time horizon, and about the method that we are using that. For example, for climate change, I have this example that imagine that we have the elementary flow of the 1 kilogram of methane, and I want to calculate the climate change of the impact of the 1 kilogram of methane. What I am doing is that I am multiplying this 1 kilogram to this characterization factor. Here, the 27 is characterization factor, but also I am also reporting the time horizon, which now it is 100. I am reporting the method that I use, which is environmental footprint, and the other assumptions that I use. So it is important to always report the time horizon and method use that we are using to calculating these indicators. Because, for example, here this 27 may vary in different methods. Now that we talked about indicators, we need to clarify two different indicators that we can calculate in the life cycle impact assessment. The midpoint indicators, which is recommended by ISO, is closer to the inventory. And you may be familiar with them, like climate change, acidification. We have other other type of indicators, which we call them endpoint indicators, which actually the main aim is that instead of reporting different midpoint indicators, we bring them as one single score and provide one single value as endpoint. So it is better for communication because you do not need to report different indicators, but the uncertainty is higher than the midpoint indicators. Two optional steps in the life cycle impacts is normalization and weighting. In the normalization, what we do, as the name is showing that, what does it do? It scales a category to a reference, which gives us the feeling to compare that indicators with other scenarios. And in the weighting, we apply specific value choices to combine categories into a single score. The main aim of the normalization and weighting is to make indicators with different units and scale comparable, and optionally combine these indicators later on to a single score. But it is, as I mentioned, optional steps. The last but not least is interpretation. Now that we calculate everything and we have our results, we need to know that, so what does these results mean to me? What can I do with these results? The input of the interpretation, as I mentioned, is all of our calculation. And the output is the validation of the results, investigating what is the hotspots and improvement options, calculating the scenarios, and clear reports for the intended audience. 3 steps is must according to the ISO. Checking the completeness, we need to check that did we do everything correct in a complete way. Checking the consistency and checking the sensitivity, which means that in sensitivity, we test the key assumption and stability of the ranking. And toolbox that we have in the interpretation step is contribution analysis, scenario analysis, sensitivity analysis, uncertainty analysis, data quality, and comparative. It is the toolbox that we have that we can use them to interpret and understand our results that we calculate better. So let's summarize. What did we do today? Today we start with saying that LCA is an iterative between the goal and scope, inventory, impact, and interpretation. In goal and scope, we define our decision context and answer that what do we want to study. We define our function, unit, system, boundary, and our assumptions, and we discuss our data quality and cutoffs. In the inventory part, we define our model unit process and flows. We define our foreground and link them with our background data sources, and we define our mass and energy balance, and we report if we have any data gaps. In the calculation step, which we call it impact assessment, we translate the flows that we collect in the inventory and calculate the impact indicators. We choose the correct and it is better to say that the most appropriate method and characterization factor for our calculation, and we report our midpoints and key drivers here. And finally, in that interpretation, we check the completeness and consistency of our calculation. We check the sensitivity and uncertainty and hotspot, and we finally conclude that what did we do in this LCA. Some practical takeaways: be careful about mass and energy balance consistent across the system. It is very important. We need to check it several times while we are building the lifecycle inventory. Always report the key drivers and limitations and be transparent. And be careful that interpret the results in the line with what was the question that was at the beginning of the LCA. And always prefer primary data and the data that you measure rather than using metadata. And be careful about mixing boundaries, that what is the boundaries that we are looking at, that if you want to do a like-to-like comparison, both of them need to have the same boundaries. Be careful about double counting, and be careful about be sure that we are comparing within the same functional unit, method, and data quality. If you're interested to go deep in the information that we talked, which we really summarized a very complicated methodology in just 30 minutes, the main source is the ILCD handbook. But there is other very interesting free course, which is a collaboration between TU Delft and Leiden University, that by clicking on this link, you can have access to that. So it is interesting. If you are interested in theory parts of the LCA, you can follow this course. Some common background database that usually is famous is EcoInvent and Gabi database, which both of them require subscription. And finally, for software, imec Net Zero, the public web app is free to use. By scanning this QR code, you can have access to it and calculate the impact of your process. There is Activity Browser, Brightway, and OpenLCA. That, again, by clicking in all of them, you can have access to their website. All of them are free, open source for calculating your LCA, and there are other commercial softwares like Gabi too. Final remarks, it is my final slice, is that is some of the limitation that we have in LCA. The first limitation is related to the complexity of LCA. As you see, it is very complicated, and sometimes it is complicated to communicate. So we really need to document everything correctly. The other limitation is related to spatial representatives. Local efforts are difficult to reflect, and many inventories rely on secondary data. Although that many times I repeat that it is preferable to use the information from calculations from the foreground, but sometimes we have to use the secondary data. The other limitation is information related to the temporal and technological dynamics. Time effects often ignored, which means that usually what we are doing is that we are comparing a technology that is now in the lab and compare it with a technology that is already in the market and it is already optimized. Usually in the traditional essay that we calculate is in this case, which is a limitation. The last limitation is related to the data and completeness, which data availability. Always data is one of the constraints that we have. Socioeconomic aspects typically is out of our scope, which is another limitation. And not all of the impacts sometimes is not covered, and the models are linear, which is the main limitation in this group. This was a very quick summary of what is LCA.
Thanks a lot, Hani, for this, let's say, more theoretical introduction on LCA. And now I will mainly discuss in this talk how we apply LCA in the context of semiconductor chip manufacturing. And so this is the outline of what I will discuss. Just wanted to quickly go through a few areas of concern for our semiconductor industry. And then I will present the model that we are developing in imec. It's called imec.net zero for IC chip manufacturing. And then we will explore a few of those results. So just to give you a flavor of what is achievable when it comes to applying LCA to semiconductors. And so starting with areas of concern, this is not really a concern. It is just a fact that our industry is really complex. So there's, let's say, there's a long supply chain now in designing new product from the design to the manufacturing of the chip to the assembly of the product, the usage, and then the feedback. And in fact, our focus will be here on the semiconductor foundry today. And if you zoom in a foundry, those are gigantic fab with very large investment, especially for the most advanced technologies. And essentially, if we look at what we call a module within the fabrication, so fabrication of a chip involves many successive modules. Typically, one module is going to be about processing on a wafer, depositing some layers, then performing a lithography to transfer a pattern on the wafer, then doing etching in order to dig through the pattern, and then clean up the resist, clean up the wafer, do sometimes a CMP to flatten everything, and then start again. And you see that this complex sequence of process will be repeated in a range of 40 to 100 times. So we are talking about hundreds or even thousands of complex, high quality process steps. And this industry is actually growing. It's growing fast. Just in terms of compound annual growth, the projected growth, and these are already numbers from 2021, but projecting, let's say, a doubling of the industry within 10 years. Also, the number of fabs that have been coming online, 300 millimeter fabs, is really high, and there's more coming. And in fact, those numbers were gathered before the AI boom that is further accelerating the industry. And then you're probably aware also of the massive funding that has come from chip acts in various countries. Now there are concerns, and I wanted to repeat here this framework of planetary boundaries, because we have only one planet. It is limited, and we have actually already bypassed many of the safe operating thresholds in the planetary boundaries. So it is a good framework to start to think about what is the impact of our activities. And here in the context of semiconductor industry, the industry is having several impacts. If we think of climate change, it is upon us. It's actually, every year has been hotter than the previous one. And in the context of semiconductor manufacturing, if we think that the humanity is emitting something in the range of 30, some numbers are even higher, actually more in the 40 gigatons of CO2 equivalent per year. The share of the ICT industry, and that is before Gen AI boom, is in the range of 1.2 gigatons of CO2 equivalent. And when it comes to semiconductor manufacturing alone, and that would be with scope 1, 2, and 3 emissions, but this is just for the high volume manufacturing of integrated circuit chip, we are in the range of 200 megatons, just to give you some numbers. And when it comes to try to understand what is the share of the climate change footprint of integrated circuit chip within a consumer product. And so here I'm really talking about consumer electronics such as smartphone, laptops, etc. We see that typically in those products, about 3/4 of the footprint is from the manufacturing of the product. This is a picture for the Apple total emission of the Apple company, and this is an independent study on a generic smartphone, but both are actually pointing to the same numbers. And about half of the 3/4 of the total footprint is actually linked to the integrated circuits carbon footprints. There is, by the way, a high uncertainty on those data, and that's what I will further discuss in the remainder of my talk. Yeah, so IC chip manufacturing accounts for a large share of climate impacts that dominates actually over product use phase in the context of consumer electronics. But there are other areas of concerns. And if we move from climate change to novel entities, for example, the concern of PFAS, it's an important concern for all industries, but also for the semiconductor industries that is using PFAS in many different areas of production. It is actually, by the way, a topic for the Genesis project. Other areas of concern would be the usage of natural resources. As you may know, in consumer electronics, we have actually many different elements that are present. And for example, here in this Mendeleev table, you can see that all the elements that are in a smartphone will have like the small white icon. And the more red they are, the more non-sustainable is the sourcing of those elements. And then a final concern I wanted to mention, it is actually the usage of water. Semiconductor industry is actually a heavy water user, and it is important also to keep that under check and to quantify the usage of water. But essentially, there are challenges, there are areas of concern, but how do we provide a quantified view on those challenges? And in Dutch, we say meten is weten, so to measure is to know. And so we want to have a methodology in order to quantify the problem. And of course, here I'm just pointing to life cycle assessment as being the methodology that you can use to establish product environmental footprint, to identify environmental hotspots in the production, but also action levers to how to decrease hotspots, to guide procurement decisions for more sustainable procurement, to optimize process without shifting burdens. That means that if you are pushing very hard to decrease your climate impact, you may create other problems and you don't want that. And then establish product decarbonization roadmap. So this is more oriented to the future. This is really about what do we do today in order to solve future problems. And so applying life cycle assessment to semiconductor chip manufacturing, this is an exercise that we have started already about 6 to 7 years ago with the development of imec .NET Zero model. Those are a couple of publications that we have, and here is also a link to the imec .NET Zero tool because there is a public version of it that you can try, and methodology is also available there. And so the goal of the exercise was originally to provide quality, transparent data on the environmental footprint. And the object that we study is a generic high-volume manufacturing plant. So here we are not looking at imec R&D fab. We are really looking into a production fab. The analysis, we also want to use it to identify the high impact problems, so the hotspots, in order to focus efforts on to improve those hotspots, and also to project the future impact of IC chip manufacturing. And we are using, as Hania presented, we are using LCA to do so. And so I will go through the different steps that Hania presented and just let's say present them with a different flavor that is more in the context of semiconductor manufacturing. So starting with goal and scope, essentially what we are going to study is well, as I said, a semiconductor manufacturing in a high volume manufacturing for different technologies. So we talk here about logic, memory, RF, imager, photonics packaging. And we are looking at multiple technology nodes, including future technologies that are not yet in production today. When it comes to functional units, typically we are going to do the whole accounting per wafer. So we are going, for example, to count kilograms CO2 equivalent per wafer. But for different users, we can actually easily transform the functional unit into a subset of, for example, per die or per square centimeter of chip, or maybe per transistor, per gigabyte of memory. When it comes to impact categories, our focus will be on midpoint impact from the EF 3.1 framework. So there are actually 16 midpoint impact. And we also include normalization and weighting, as Hani already mentioned in her talk. When it comes to the flow, we are really going to focus here on in this system boundary. The foreground will be really wafer manufacturing in a semiconductor foundry. So we are going to look into all the wafer processing equipment operations, so all those big equipments that are in the clean room, but also everything that's in the sub-fab that generates utilities such as cooling water, such as ultra pure water, compressed dry air, nitrogen, and things like that. And we will also look at the whole infrastructure operation. So we are really looking into the full manufacturing fab. And so we have a foreground, as Hani presented, but actually our analysis expands to provide a cradle-to-gate silicon chip manufacturing, where we're also going to capture a background that includes all the sourcing of the chemicals and the minerals that go then through a transformation chemical industry before they enter the foreground, the manufacturing chip. We also look into packaging before we release, let's say, a fully packaged a chip that is then going to go into a system, and that is outside of the scope of our analysis. What we do not include, by the way, at the moment, it is the manufacturing of the equipment and of the infrastructure. And so it's just a view again on lifecycle inventory now. We want to record, as Hani presented, all the input and output flows. And this is a picture I like to distinguish what's going on in the ecosphere. So those are all the natural services from our planet that we get for free. And then the technosphere would be, let's say, the whole layer of industrialization that is from humankind. And in fact, our semiconductor foundry will be part of the technosphere, and it is included into this foreground boundary. And in this activity, there's a lot of stuff going on inside the fab that we are going to try to capture. And essentially, we will also, when doing the big inventory accounting, we will capture all the inputs in terms of energy. So that's essentially electricity coming in, all the transform material inputs, but we will also count all let's say, the waste that will have to go to a treatment plant before releasing the ecosphere. But also everything will be accounted for one functional unit, one wafer being produced. And of course, in the accounting, we also need to take into account the exchange with the ecosphere. So primary energy inputs, that could be solar light that is radiating on your fab, raw material inputs, and then there will be emission to the air, and for example, greenhouse gas emitted by the foundry, but also liquids and solid release to the river, for example. Another way to look at this, and just to start to digging a bit more, you can recognize the same canvas here, and we are going to count, let's say, all those flows, and that's really the goal of the inventory, to account for all those elementary flows to the ecosphere, and then all the intermediate flows from the technosphere and back to the technosphere. And so typical flows that will be input energy that we count in kilowatt hour per functional unit. Input consumable, output waste. We do a big accounting that's based on primary data, and Hani has been providing a good description of everything that you need to track in order to build the inventory. And essentially, we are building a big bill of material. And then the following step will be on the impact analysis. And there I just wanted to distinguish maybe what is necessary to characterize the elementary flows. So those are the inputs from ecosphere and output to ecosphere. So for example, the greenhouse gas emission from the fab chimney will be part of this. That, as Hani presented, and we need to classify, and then we need to characterize it. Whereas the other element that we need to characterize will be intermediate flows. Those are input from technospheres, but also output to technospheres. So that would be, for example, all the chemicals or the electricity that come in your fab. Output to technosphere would be, for example, waste solids that need to go to a treatment plant. And there we will need to determine impact factors. It's also sometimes known as emission factors to understand, okay, the sourcing of that chemical or the embodied emission of manufacturing that chemical in the supply chain is that much. And essentially, after the characterization, we are mapping those on midpoint impact, as Hani presented, that could be aggregated into endpoint impact. And so characterization factor, you should really see that as a physical parameter that's coming from environmental science to quantify an impact that is caused by the addition, withdrawal of a substance to or from the ecosphere. And a global warming potential is a well-known characterization factor. It is actually a combination of radiative forcing from the let's say infrared radiation that's coming from the planet, plus the atmospheric lifetime of the greenhouse gas species. And so the combination of the two is actually giving you a global warming potential that is going to be, for example, in CO2 equivalent emission per kilogram of the emitted gas. And then on the other hand, the impact factor, that's really a parameter that qualifies the impact of procuring or releasing a synthetic substance from or to the technosphere. And so this is really, essentially to determine those impact factors, you need to perform the LCA of the supply chain itself. And typically there we can, that's not something that we are able to do ourselves. Our focus is really semiconductor foundry. So we are going to rely on LCA database and we will handle their secondary data, as also Hani explained. And so if we take the full picture, then to determine those impact factors, essentially this would be the problem that you need to solve. You are not only studying the foreground in full details, but ideally you would like to understand what's going on in the supply chain. So upstream of your fab, there's a complex sequence of process. And of course, it is not possible to know all of that. So we will need to rely on secondary data in order to characterize this. But believe me, this is also a big portion of our activity to get or to improve the quality of the characterization of the supply chain upstream, but also the supply chain downstream, for example, with a waste treatment here. And then a few words on impact categories. So Hani already went through, but now I'm just mentioning here that in the context of imec.net zero, we are actually sticking to this environmental footprint 3.1 framework that is actually coming from the European Commission. And that one defines 3 endpoints, so human health, natural environment, so the ecosystems, and also natural resources. And there are 16 midpoints indicator to capture a broad diversity of impacts. This is the list of the 16 midpoint indicators. And you see that those different indicators feed into the different endpoints. And also I found it interesting that in this picture, you see that it can also link back into the planetary boundaries. So that would be actually in the red lettering here. So everything is interconnected, but it's really always depends on how you are looking at things. And so we are implementing EF 3.1 in our modeling to really provide a full impact analysis that is going beyond climate change only. Finally, a word, so now I just mentioned EF 3.1, that is one framework to look and interpret your results. Another one that is very famous is the greenhouse gas protocol. That is a method to report greenhouse gas emissions. So you may be familiar with the scope 1 emissions. That will be the direct emission from your activity. So for example, the greenhouse gas emitted by the chimneys of the foundry. The scope 2 are the indirect emission from manufacturing electricity that is feeding into your main activity. And scope 3 would be all the other indirect emission from the upstream supply chain, but also from the downstream activities, depending on the boundaries that you have. Note that greenhouse gas protocol is really only climate change. It is useful to establish product carbon footprint, to do, for example, corporate carbon accounting, but it's really limited to only climate change. As soon as you want to embrace the complexity of impact, you have to move to a different framework. And finally, and I think Hania also did a pretty good job to show you that this, LCA in practice is complex. It is the preferred method to get a quantitative environmental impact assessment, but you need to be very systematic, very transparent, and then you need to collect a lot of data, especially when you are dealing with a complex production such as semiconductor production. And indeed, there are large-scale data sets such as EcoInvent and software, as Hani already mentioned. And so now moving to the implementation of that methodology in lifecycle assessment, essentially, and just to put it very simply, what we are doing, we are building a bottom-up lifecycle assessment view where the fab is the foreground. And essentially, we are going to collect data. We are going to collect data on all the tools in the fab. We collect data on all the process running on the tools and all the materials that are being used on those tools. We are then also, and you can see that as the ingredient of your cooking recipe. And then we have recipes to assemble those processes together. For example, we are going in our assessment to cover logic nodes from older node to node that are not yet in production. DRAM, 3D NAND, and other technologies are covered. And that's an important layer. We need fab modeling in order to provide a realistic picture of what's going on in the fab. So it's just not assembling what's going on in the clean room tools. You need to understand what's going on in the sub-fab, the timing of the wafers in the fab, the quality of the abatement or yield questions are very important. So that there are many different fab models that come on top. And so when we assemble all of this, we actually come up with the inventory of IC chip manufacturing. Just a word on fab models. There are many fab models that are running in imec.net Zero. You see die placement model. We have fab dynamics. We have abatement. And we are publishing the full methodology behind imec.net Zero on the imec.net Zero website if you are curious. There will be a lot to say on fab modeling. And then next, what we will do is the impact analysis, where essentially we are going to characterize the inventory using a number of characterization factors and impact factors to characterize the intermediate and elementary flows of the inventory to finally produce a vision on the impact of IC chip manufacturing. Since we do it bottom up, so we are really working from a process step level and upwards, let's say, to represent a full fab, we have a high granularity. So we can really decompose results with high granularity. We can perform sensitivity analysis, and we can also do pathfinding because we can represent things that do not exist yet. And so to show you the power of the approach, I just wanted to have a logic technology exploration here. So essentially, all the results that you will see in the following slides, they have been modeled in imec.net Zero using those default assumptions. So we are looking at 10 by 10 millimeter dies with a IPCC T2C abatement model, et cetera, et cetera. And essentially what you see, if we are modeling the full progression of logic technologies from 90 nanometer, that was the first technology manufactured on 300 millimeter wafer, to N2, which is today the most advanced technology produced in TSMC. And here we look at, in the greenhouse gas protocol, at scope 1, 2, and 3 emissions together. You can see that as you are increasing, let's say, moving to higher and more modern nodes, we increase the complexity, and essentially we increase the footprint. You can also see there's an interesting moment here between N7 without extreme EUV lithography and with extreme EUV lithography, where EUV actually, although it's a complex technology, really helped to reduce the total number of process steps. And so it gave let's say a shrinkage here at N7, but also had to not accelerate as fast if we didn't have EUV lithography. But now if we talk about increasing complexity in logic nodes, we are talking about more process steps as we move towards 2 nanometer. We talk about bigger clean rooms. So you can see here, this is in square meter of clean room area. And all of this is calculated, by the way, for 60,000 wafer per month fab capacity. We have also more tools in the bigger clean room. We are using more electricity per node. We are using more water per wafer, and there are also longer cycle time with moving from 50 days of production to 120 days of production. So another thing that can be done with this bottom-up LCA approach, it is to decompose the results and really to start to explore the granularity. You can actually break down, for example, the impact itself. So here, instead of looking at the total climate change, we can decompose between scope 1 direct emission, scope 2 related to electricity, and scope 3 from the supply chain. And you can see, for example, that the importance of scope 2 emission is increasing over the nodes as equipment are actually consuming more power. And then we have a breakdown here, breakdown the process flow. So you can actually decompose your flow between back end of line, front end of line, and middle of line to see how those different flows are evolving. And you could see that in the early days, for example, the importance of the front end of line was actually increasing. And then another way to break down the results would be here where you can decompose between the different areas that are in your fab, and then you can try to interpret your results as a function of where they are being, for example, here where the carbon is emitted. Where you can see that the importance of dry edge department used to be about a quarter of the emission in the older nodes, but has seen a relative decrease, whereas actually the litho has seen a faster increase towards the more recent nodes. Another thing that you can do, it is instead of looking only at climate change, because so far the slides I showed were only about climate change, we want to embrace more impacts. And so we are looking here at the 16EF 3.1 impacts. This is a full slide where we put all the impacts side by side for 3 different technologies. And you can see that in this case, in order to represent them on the same scale, we had to normalize and weight. I will not detail the methodology of how we do that. It will come in a later webinar. But essentially, you can see that after normalization and weighting according to EF 3.1 protocol, climate change is actually the dominant impact, followed by the fossil resource depletion, interestingly. And so then we can again zoom in into different impacts and to start to represent them. For example, resource usage of fossil is expressed in megajoule per wafer, whereas the abiotic depletion potential will be represented in milligram antimony equivalent per wafer. But you can see again under those upward trends are again observed for the other type of impacts. Finally, I wanted to say a word about functional units. So far I've been showing only results per wafer, but maybe depending on what is your job and what you are optimizing, you want to look at the results with a different lens. And for example, here I'm showing a different example of functional unit. This one would be kilograms CO2 equivalent per square centimeter of yielding die. So this is after cutting the wafer into your dies. And so we are going to allocate all the emission of one wafer to divide it between all the dies that have yielded. Another view would be the total emission in ton CO2 equivalent per month of fab production. And here we are talking about much more massive numbers, of course. And finally, an interesting functional unit, just to provide an example, this is kilograms CO2 equivalent per mask layer per square centimeter. And essentially, you see a relatively stable value of about 20 to 30 grams CO2 equivalent per litho mass per square centimeter. That actually is useful to compare different technologies of different generations, and even actually technologies produced in a 200 millimeter versus 300 millimeter fab. So functional unit can also be carefully chosen to enable you to compare results between things that a priori are not comparable. A word on sensitivity analysis, because the tool also enables to systematically vary some of the model parameters. And so here you see 2 variations, one on die size, where we actually increase heavily the size of the die from a tiny 1 by 1 millimeter die to a very large 25 by 25 millimeter die. And you can see that the scope 1, 2, 3 emission, kilograms CO2 equivalent per die, actually exponentially increases with the die size. And that's really related to yield modeling, where large dies have a much worse yield than very small ones. And then also looking here at a very different sensitivity analysis. This is on greenhouse gas abatement deployment. You have a fab here with 0 abatement. We are not burning the greenhouse gas before emission. And here there's a full deployment of abatement. And you can see the importance of abatement, that you can actually really drive down for 2 nanometer here. You can really drive down scope 1 emission, direct emissions really heavily, thanks to abatement. And by the way, what remains here at the end, there is still a bit of greenhouse gas emission, but it's also related to the emission of fluorinated heat transfer fluid, which is a different problem, but also contributes to direct emission of a fab. All right, this is the last slide on the results. So this actually brings me to the conclusion. A few take-home message is that first, the impact of IC chip manufacturing is one of the largest contributors to the carbon footprint of ICT devices. Those are low entropy products from highly complex value chain. It is actually one of the highest carbon footprint per mass ratio. So it's a tiny object with a heavy carbon footprint. It consumes massive amount of electricity and high purity materials. And when it comes to LCA applied to this industry, it is a powerful tool for science-based decision. It provides a detailed quantification of impacts, and it can be a tool to drive change in innovation, in design, in procurement. But of course, in order to enable that, it is really a complex story. You need to perform the inventory of a complex fab. You need also to do the characterization of a complex supply chain. And if we want to drive change, because it would be our objective here, we need broad user adoption. And essentially, this is also part of this Genesis Task 1.3 ambition. It is to facilitate LCA in semiconductor R&D. And so with this, I just wanted to, we have presented today this LCA basics, but next time we will actually deep dive into how we do the characterization of the bill of material. So how do we address this supply chain question? Finally, the work, Hania and I, we belong to this SSTS program in imec. So it stands for Sustainable Semiconductor Technologies and Systems, where we are actually working with many partner companies. And our goal is really to help the IC manufacturing value chain to reach its environmental sustainability targets. So we do a lot of assessment. We also drive R&D in imec fab to address hotspots. And with this, I want to acknowledge, of course, the Genesis project, but also the FAMES project is also supporting this work. And so thank you for your attention.